Okay, hi. So today the plan is to continue our discussion about computer architecture, and we have a very interesting topic for where we start today and we continue next week and maybe the week after that. It is one of the most fundamental models or ideas in computing overall, which is one Neumann model based on which modern computer has been built. We'll also continue discussion about instruction set and two particular computers based on one Neumann model, LC-3 and MIPS. LC-3 is a structural computer, is very small in terms of instruction set, but MIPS has essentially shifted into many different products, so it's more real world, and we plan to discuss about all of these in the next few weeks. So before I go into the detail, do you have any question for me about anything? I also sent out the syllabus. Hopefully we'll set up the course website soon. But for now, you have the slides and everything. So yeah, and I plan to give you some quizzes regularly as we go. So you would learn based on these quizzes, questions. I will try, as I said, on Gradescope, see how it goes. Hopefully it works. We tried in AI course before. It was very useful. Let's see whether for computer architecture it also works, and how useful would it be. Okay. So the agenda for today is to discuss basically the foundation of one Neumann model, and we have some examples based on LC-3, which is a particular instantiation of one Neumann machine. Also, we'll discuss MIPS as well. For you guys, especially when it comes for assembly programming, you don't need to know or learn much about LC-3. Your projects mainly will be based on MIPS ISA, because that's more realistic, more popular, but essentially having these two machines and discussing about similarities and differences is a way to learn computer architecture better rather than just focusing on one particular machine. And that's why I decided to have both of them. So this contrast basically gives you the opportunity to learn much deeper, especially when it comes to contrast and similarities, differences, trade-offs that each machine make, essentially. And then later on, we will continue with more advanced topics. Essentially after we are done with these two essentially machines, LC-3 and MIPS, we'll do some assembly programming. We'll have several examples. And after all of these, we continue to discuss about microarchitecture. I briefly mentioned this relationship before about this level of abstractions. Hopefully you remember that. So microarchitecture essentially is a particular implementation of instruction set. An instruction set is the contract based on which programmer interact. So it's a contract that programmer writes program based on these contract, these instructions. Programmer doesn't need to know about the detail below this, below instruction set. But for you, in order to understand this deeper, you need to know the foundation of how you can implement a particular microarchitecture, what are the trade-offs, and so on. So, but this will come later and in several following weeks, not yet. So today, we'll discuss in particular LC-3, and we'll discuss different instruction, like operating instruction, data movement instruction, control instructions, some formatting, some addressing modes. Let's see how much time we'll get, but hopefully we'll cover these stuff as much as we can. So let's start with the von Neumann model. So essentially, this is basically this course is about building computers, right? For building a computer, we need some elements, some components. These components are basically decision components and storage components or elements, however you want to call them. With these two elements, essentially, you can build computers. As long as you can orchestrate these two components well. So you need a particular model to orchestrate these two elements in order to build a computer. You cannot randomly put these together and build a computer. You need a model. And hopefully you remember the roots of these elements from digital design course, that you can build these elements with combinational circuits and sequential circuits, which gives you the capability of decision and storage, and you can build with these components with different complexity of different nature. And we discussed last lecture, essentially, we need to implement a particular task for the computer, and we have a problem and we want to solve this problem, so we need to write program in order to get this task done. So we need a computer, we need a data, and we need a program in order to accomplish a task. And with these, obviously, you can implement a task. And you know that program is a set of instruction. An instruction essentially is the smallest piece of work in a computer. instruction is the fundamental or the smallest piece based on which the programmer can write program. We discussed like we have a smaller units than this, like we have like atoms, electrons, but we don't want to talk with electrons directly. That makes writing programming not fun, very complex. So, and that's why, and that's the key reason, essentially, and that's the key enabler for this level of abstraction is the key enabler for writing complex program, which would otherwise was impossible. So in order to accomplish, implement complicated programs, this level of abstraction helped a lot. Like we couldn't write a very sophisticated program if we wanted to write it in terms of circuits, right? Even higher than you know, electrons. So this level of abstractions, having the capability to have some abstract instructions, is the key enabler of the whole computing. And you got the chance to learn about power of abstraction in other courses as well. In this course, like we came here, like we plan to go deeper, but in other courses, you also got the chance to learn about these, how useful or how powerful is abstraction in computer science, essentially in data structure. For example, you got the chance to build more complicated data structure and write more sophisticated programs. Here is like the same. We have multiple level of abstractions, but obviously like at a lower level. Okay, so let's start building some computer together, hopefully. And obviously, as I mentioned, we need a particle model, and this model has been proposed. This fundamental model has been proposed many years ago in 1946 in a seminal work by von Neumann in this particular paper. This model has been used and still modern computer is implemented by von Neumann model, makes a few domain-specific architecture, domain-specific computers, you could say, that do not follow, for example, von Neumann model. And we'll discuss briefly some of those later on. So this model is really simple, and you are already familiar with it to some extent. It has 5 different parts. It has memory, it has processing unit, it has input, obviously, output, and control unit. So like it consists of only these 5 parts. And as I mentioned, we plan to discuss these 2 examples of instantiation or implementation or realization of von Neumann model in real computer, LC-3 and MIPS. So LC-3 is a lot simpler, and MIPS is more complicated and like real world computer. So one Neumann model is as simple as that. Probably you saw this diagram before in other classes. So you have memory. In memory, you have two particular registers. We'll talk about it. Memory address register, memory data register, and some other components, as you see, as we discussed, input, output, you're already familiar with it. Processing unit is the part where all these mathematical operations that you need for any arithmetic is implemented there. And control unit is essentially orchestrating all of these. So is the key piece here for basically orchestrating all of these components all together. Do you have any question before we move on? Hopefully it so far is easy and clear, and we plan to clarify, to go inside each of these to some extent and understand them better, how it works. Essentially, the orchestration of these parts is what is based on which you can build computer, right? So essentially all of these, what you see in all of these components are some, inside each of these are some circuits. The orchestration of these, what it enables us to build a computer that we can write programs and it can execute program for us. So the memory is important. It stores both data and program itself, and it treats them the same way. So memory doesn't differentiate between data and program. It's a bunch of data, 0 and 1s, which are stored in memory. So essentially, memory itself doesn't understand the difference between these two. Is linear, only contains bits, and bits are grouped in bytes. You already know that, these foundations, and words. And the size of word really depends on a particular microprocessor. So essentially, this is the way how you address memory, right? So you need some addressability. You have different model for addressing memory. You have word addressable memory, which is essentially it depends on the size of each word. So it could be 8 bits, 16 bits, or 32 bits. If your memory is word addressable, and could be your memory also could be byte addressable, in which you address memory based on 8 bits is constant. So essentially, this addressability of memory is the way how you interact with the memory, is where how you see the memory, how you can read and write inside the memory. So it's two different models of addressability. And the total number of addresses obviously depends on the address space. In LC-3, we have 16-bit addresses. So we have the total size of the address space is 2/16, obviously. And in MIPS, we have 32-bit addresses. And obviously the total size of the memory is 2/32, is 4 gigabyte, right? LC-3 is 46 kilobytes, right? And in modern computer, x86 64, the address space is 2/48. Essentially, this determines like how much memory you have and how large the memory that your computer could work with looks like. So in word addressable memories, each data word has a unique address, right? For example, in MIPS, which each word is 32-bit. Each address, essentially, this determines how large each address of the memory is. So, for example, the first 0 address consists of 32 bits. The same for the first, second, third, and in LC-3 is 16-bit wide. Visually, this is how the memory looks like in MIPS memory. So word number 0, you see that it is how large it is, word number 0. Do you know the representation down there in the memory? What representation? Yes, go ahead.
Is it coded in hexadecimal?
Correct. Yes. Hopefully, you are familiar. You should all familiar with this different number systems. This is hex representation, and you know that you know how to interpret hex representation, right? So each 2. So in total, you have how many numbers here in each address? You have 1, 2, 3, 4, 5, 6, 7, 8, right? And each number is 4 bits. So in total, you have 32 bits here. And this determines how large each word is in MIPS memory. And by convention, you have address address word number 0 at the bottom, and you go up, the address would increase. This convention you could do the other way around, but this is the model how everybody works with. A convention memory is linear, and from it increase, the addresses increase from bottom to the top. Any question about this? And this is how it looks like, right? This is the actual addresses, the word addresses. So you see 0 at the bottom, first, second, third, and all the way up to the level that your ISA can support. So for MIPS would be up to 2/32. For LC-3 would be 2/16. Okay, that was word addressable memory. Byte addressable memory, in byte addressable system, each byte has a unique address. For example, MIPS is byte addressable, and one particular version of LC-3, which is called LC-3B. The original LC-3 is word addressable, but this extension of LC-3B is byte addressable. Here you see that each, again, at each row you see 32 bits, right? So the addresses that you see on the left-hand side points to the particular address, byte address in the memory. So in the first row, you see already you have 4 bytes, right? EF is byte number 0. I'm seeing the lowest row. CD is number 1. AB is number 2. 89 is number 3. And basically the second row start with number 4. So each byte address points to the first location, essentially, in the global address memory. So hopefully this is clear. Essentially points out to EF as byte number 0, but I think you should have heard about this, that you have 2 different models, big endian and small endian, but I will discuss it a bit later. Big endian is the model essentially where your right hand, essentially, like, this is the story. So at each memory address, you have the least significant byte and most significant byte at each row, if you look at it. In little endian, which is more popular and more usual, number 0 start from the least significant byte. So from right here, 0, 1, 2, 3, but in big endian model, the first addresses start from the most significant byte. So you see that on the left-hand side, the first address is put on the most significant byte, and as you go to the right, 1, 2, 3, 4, 5, 6, 7, and so on. So hopefully this is clear. And essentially, really, it doesn't matter as long as you want to locate a particular data in the memory. Only it matters when you want to communicate between two systems. In that case, obviously, if you have one node with little endian, one node with big endian, you need to know how to transfer data and translate these two different systems, which would otherwise make some, you can interpret incorrectly the data. Okay. Any questions so far? Hopefully these are not very difficult. So let's talk about accessing memory. There are essentially two ways of accessing memory. You already know that. You either read the memory or write. Is sometimes reading called loading data from memory, and writing is called storing. That's somehow convention, also may help you to interpret the assembly instruction better. And we have two registers in this von Neumann model to access the memory. You will see this in the larger model, MAR, memory address register, and MDR, memory data register. And we'll discuss about these two a bit later. So to read, like you need to do a few steps. First, you need to load the address to MAR. So you need to first tell where do you want to read from the memory. So you have an address, you need to load it to MAR, memory address register, and then data will be placed in MDR, memory data register, where you can read the data from, right? So for reading, you have an address, you want to see what content this address has. So you need to put the address inside MAR, memory address register, and you need to get the data from MDR. Essentially, this data will be placed on MDR register where you can read. And for writing, very similarly, you need to load the MDR with the address, and MAR with the address, and MDR with the data, and then you need to activate this signal, enable signal to tell that, okay, it's ready, and go and write this particular data point to this particular address in the memory. So this is simple as that. So you have two particular register where you can use for reading from memory. Obviously for reading, again, you need an address, and you can retrieve the data from another register, memory data register. For writing, you have a data, you have an address, you put them in these two register, and you tell, you activate the enable signal in order to get this task done. This is what you see in the memory, right? So you need to have these two register in order to do these operations: memory address register and memory data register. Okay, these were the memory, what you needed to know about the memory. And for processing unit, so you see that here the ALU, arithmetic logic unit, is located in the processing unit. Is the unit that the mathematical operations will be performed. This processing unit already basically beside ALU, it has other components, but essentially arithmetic and logic unit is the most important component in this processing unit, which execute the computations that you need. And like for each particular computer, for each particular ISA, you have like these building blocks, right? These instructions essentially. For LC-3, you have add, and not, and in the LC-3B, you have XOR as well, and in MIPS, you have much more. So you have add, subtract, multiplication, and NOR, shift left logic, shift right logic, and so on. We'll discuss about the detail, but for now you don't need to know about this, but essentially these are the instruction that that existed in or implemented in ALU for each particular computer. And ALU processes these quantities basically referred to as words, but like for example, the word length in LC-3 is again 16, in MIPS is 32 bits. But and this size, as you know, might vary depending on particular implementation of ALU. And you also have some temporary storage, and this is also very important. Particular registers that you need to have in processing unit in order to manipulate the data. So these operations, add, subtract, multiplication, all of these, they need some operand, and these operand are basically use register in order to specify this operand and manipulate the data, because it's a lot faster. This is like how instead of directly working in memory, you load them into this register, and you do this calculation with these registers. These are particular temporary storage, very close to the processing unit, inside the processing unit, essentially. And yeah, you know that, like, for example, for calculating a particular expression, in this case, a plus b multiplying by c, like you can calculate the a plus b and put it inside the storage in order to later on multiply it by c. So these registers essentially are typically used for storing these temporary values. So memory is big. Registers are very small, limited, but a lot faster than memory. And by convention, each register contains one word. So the content of each register is one word. And you have a particular register set or file in LC-3, or basically LC-3 computer has 8 general purpose registers, which are called R0 to R7. And you can, that like with 3 bits, you can represent these 8 different registers, and each of these contains one word. And you know that word size in LC-3 was 16, right? So the MIPS, on the other hand, has 32 bits for each word, and that's what the register size of MIPS is. So these are some basic definition. And these are, like, for MIPS, these are all 32 different registers that you can use for different purposes. Like on the top, you see $0. $0 is a very specific register which represents number 0. You cannot change this register at all. You cannot load number inside this register. It's only used for representing 0, very special purpose. The other ones have general purpose usage, so you can use for different purposes. By convention, you use, like, for example, $add for assembler temporary values. V0, V1, you use it for function return value. When you write a function in assembly, you use these for returning the value from a function. For writing again function, you need some arguments. You use A0 to A3 for function arguments. And if your function argument is larger than this, we'll discuss like how you can deal with that. What you can use. You have some temporary variables, T0 to T7 and some others, right? You have also like down in the table, you have function return address, where you can find when your function, when you calling a function and when you return where you need to go, what address you need to go, use this register. Frame pointer, stack pointer, global pointer, and so on. We'll discuss about this later on, but you don't need to be worried about memorizing them. And essentially, you can treat these variables differently as well, but these are conventional usage of these registers. So in other words, you can write anything inside this register. But these are like conventionally, this is the way how you should use it. And beside processing unit, so we discussed memory, processing unit, input output also are easy. The keyboard, mouse, disk, you're familiar with this, so it's not very complicated. These are some peripherals that you use for either inputting data or outputting, seeing the data. These are very much clear, so we don't need to spend much time on this. You are familiar with this stuff. But the most important unit in one Neumann model is the control unit. Essentially what it orchestrates all of these units in order to enable the program execution. It's like a conductor of orchestra, right? So it conducts the a step-by-step execution of a program. So it helps you to execute a program step by step, and it keeps track of the instruction being executed with a particular instruction register, IR, which essentially contains the instruction which is being executed in the computer. And then another register, you probably have heard about it, like program counter or instruction pointer, is basically points you to the address of the next instruction to execute. So hopefully these two clear, right? Instruction register points you to the current instruction, PC or IP, like next instruction. And this is the state of the system from the programmer's perspective. This is what programmers see. So it sees memories. So you have an array location of memory addresses. You have registers that you can read and write. right? Depending on the ISR you discussed, like you might have different type of registers, different number of registers, and you have program counter which point you to the next location where you need to the computer needs to execute. And essentially your program changes the state. So the way how you can look at it, your computer goes from one state to another state by changing the value in either of these locations, right? Memory, registers, or program counter. So this is the whole model of what is called von Neumann model. And essentially in this lecture and the next few weeks, we'll focus mainly on these components inside particular implementation of this model, LC-3 and MIPS, essentially. But this is the whole framework or model that you see inside this realization, inside this basically implementation of this model. And like the key enabler or the key properties of this model is essentially two things. And this is very, very important and was the key ideas that enabled building a computer is a stored program, essentially being able to execute, being able to store program like data is one property. Sequential instruction processing also is being able to execute what you stored in the memory. So in a stored program, you have some instruction which you stored in your memory array, and as I said, your memory doesn't differentiate between data and instruction or program. So it's a some bunch of 0 and 1s, right? But but this implementation gives you the ability to interpret these different locations differently. Either you can say that, okay, this location contains an instruction, this location contains a data, right? So the way how you can interpret the value is what you can, how you can essentially differentiate between what is data or what is instruction inside the memory. So this capability of differentiating these two is a way to execute the program. So you have a unified memory, then you can interpret different part of the memory differently. This is the way how you can execute your program. So you have a stored program and you have sequential instruction processing where you can fetch, execute, and complete instruction based on the particular location of the instruction, right? This program counter identify the current instruction and advances sequentially from one instruction to the next. So these two key properties: a stored program, being able to store a program in the memory and being able to execute sequentially is the two key fundamental properties of this model. And the whole units, the way how these units are orchestrated together essentially provide or implement or characterize these two properties in order to execute a program. Any questions so far? Please don't be shy. If you have any question, you can definitely interrupt me and ask. This is, hopefully I'm not too scary. Let's look at inside what is in LC-3. This is the way how LC-3 is implemented, and you see these 5 units in one Neumann model already here, right? You have input, output down there. You have memory again down there. You see MAR and MDR, how these are connected to the memory. So these are particular registers where it's directly connected to the memory because you need to have like particular address in MAR to locate in the memory, and MDR is where you put the data and you're able to read from it, or for write, you're able to store inside it and write it inside the memory. And up, you have control unit where, as we discussed, is controlling or orchestrating the whole thing. Processing unit, ALU, you see on the right-hand side. So these are a bunch of different circuits which are, again, connected together in a orchestrated way according to one Neumann model in order to implement a computer. And like you see a bunch of different things, like you have some control signals here. So here you see a particular multiplexer, right? Where based on this control signal, essentially you tell, hopefully you know what multiplexer is. Based on this control signal, you tell it which input to choose, right? So you already see that essentially program counter needs to typically go one by one, right? This is, you see here, you need to add one into program counter, right? And sometimes maybe not, right? This is what you have the other input because you want to maybe jump to another location, right? This is why you need multiplexer here to choose from. You have also many different components that will we'll discuss, right? So we have again, memory is 16-bit addressable, right? We discussed this in LC-3. You have MAR here, you have MDR, you have input, output, you have ALU, which has 2 inputs, right? And 1 output. Typically for all of these operations, you needed either 1 or 2 input. That's why for one of these you have multiplexer again. And then these are your registers, your 8 register, which are located here in this component. You have instruction register, where essentially tell you what instruction you want to execute, and you have this program counter, and you have this finite state machine. Essentially, hopefully you know what is finite state machine. In other courses, is basically generating the control signal. Is a key component in control unit, essentially. And yeah, you also see some other components here, like these gates, and these gates have a specific purposes. Essentially, you have a processor bus here, a bus. What you can write and read from bus to move data between different components, and these gates essentially control whether you put data inside the bus or not, right? So these gates control this, and you see that for each gate you have some data coming, like up there you have, down there you have like gate which is coming from ALU, is the result of calculation. This is like, for example, when you use add, this is the result of adding 2 numbers, right? And you want to put it inside the memory, so you put it in the bus, and then it goes to MDR, right? To in order to be saved in the memory, if you want to do that. And this gate basically have a enable or disable, and that comes from this finite state machine. You see that this input basically controlling whether it is enabled or disabled. So if enabled, you can write. If disabled, you cannot, right? The same for up there for gate PC. You see that when it is needed to write the value of a PC inside this on the bus, essentially. Any question about this? So this, again, the bus is responsible for moving data between different units, right? And you see like what components, how they have access to the bus, right? So for output, you want to read from bus. For input, you write to the bus, right? We discussed about ALU and program counter, and also you see some connection from the MAR and MDR. You have also a gate for MDR whenever you need to write to the bus. This gate essentially provide mechanism, and you already know how to implement this from digital design, which we are not going to talk about it now in this course. But these are all components which enable a very simple computer like LC-3 exist. Obviously, you need ISA to have some instruction and so on, but essentially this is how the model look like. So instructions are and data are stored in the memory, and like this instruction, again, like the length of the instruction or the word length. So the processor fetches this instruction from the memory sequentially. So it means that like one instruction at a time. So it fetches one instruction. So you need to decode and execute the instruction. And then you need to continue afterward to the next instruction. And this is like the generic process for executing the instruction, right? So you need to first fetch the instruction, and then once you fetch it, you need to see, okay, like what this instruction mean. You need to have a way to interpret it. Again, like the way how you interpret it, it comes from your ISA instruction set, and you need to execute the instruction and continue with the next one until you're done. We discussed about PC. So in word addressable memory, like LC-3, the program counter is incremented by 1, and you already saw this in the implementation here, right? So you see that this one here. So PC is incremented by 1, meaning that this is word addressable. In byte addressable memories like MIPS, since each word is basically 4 bytes, again, like 32 bits means 4 bytes. So program counter needs to be incremented by 4 at every single iteration. And you saw that in the memory addresses, so it increments by 4. So again, it really depends on the type of addressability of the processor, of the memory. And in MIPS, by convention, PC initially sets to this particular address in the memory. This is where your program instruction started or located. And yeah, this is like one example of a program in MIPS assembly. Again, this is very simple. We don't need to know this. We will discuss like the meaning of these later on, but just wanted to know that like the connection between assembly language, because again, like high-level language, this is a language which has been constructed for us programmer to write machine code, because machine code is like this. We cannot. It's very difficult to write code like this. But essentially, these code will be translated into machine code, and this is how it is represented. So for each instruction, like the first one is, for example, like one assembly code loading a word. So for that, you need a particular address. So you see that it is given a particular address, 32, and then you load and put it into register number T2. For add, again, you have 2 operand, S1 and S2. You add them and put it in S0 and so on. Like, so this is the some instruction in assembly language where we will discuss later on, and this is the way how you store this program in inside machine, right? So this is your machine code, and this is your memory. So you see that by convention, again, from the bottom, you have the first instruction, like it start 8C, 0A, 0020. And next one is the next instruction, and so on. So this is how you see the memory, how this machine code is located or stored in the memory. Again, this is one of the so if I ask you what are the 2 key properties of one Neumann model, is boiled down to 2 things: being able to store program inside the memory, as you see here. So here you see that we have a stored program in the memory. And we also discussed the way how essentially we can execute sequentially a program, right? So we have a program counter which starts at a particular location in the memory. So it starts with a particular address. We have this address, right, where we start, and then once we fetch, we execute, interpret, and execute the first code instruction. We go to the next. PC moves on to the next, and essentially the program gets executed on the machine. That's essentially all you need to know about one Neumann model. But we are going to have much more examples essentially about the instruction set. Now we are, since we know what one Neumann model is, we have some intuition about some implementation of one Neumann model. Now we are ready somehow to discuss some particular detail about the instruction set. What are these instructions, how we can interpret them, how we can write program with them, and so on. But let's stop here. And next week we will continue the discussion about instruction set, and again, after that we'll move into microarchitecture, more interesting stuff. But we have like a few weeks to deal with the assembly stuff. I stay here for a few minutes. If you have any question, I would be glad to answer your questions.